Good. We are here and we have one more student joining us. That's the syllabus. And let's get our notes. November 18th, 2024. This one is 2023. It goes. Let's see where we stopped. That was the lab. And here is chapter 6. Okay, and let's copy this thing and paste there. November 18, 2024. I wish I could, let's say 6.1, huh? Let's see if it works. Yeah, it does. Now 6.2, good. 6.3, 6.4, 6.5, 6.6, 6.7, 6.8. We are going to skip 6.8. And finally 6.9 plus lab exam 3. Material for exam 3, which again is scheduled 27th, right? 11, 27, 24. And 3 on. So far, right? So far we have the following material for exam 3 on November 27th. Let's make sure it's the 27th. Yeah, 27. And let's do some examples now for conservation of energy, right? Okay, yeah, that's, I'm gonna do a very simple example, example involving potential energy. Gravitational potential energy. No potential energy. And this example is very similar to something that we have solved before. Okay, this example This example can be solved using kinematics, but for the sake of using the concepts I introduced to you, we will use the concept of chapter 6. Okay, so here you go. And I'm gonna need my illustrations as well. Work. Uh, hmm. Yeah, I'll have to. Okay, we can use this one right in here and slightly modify it. Okay, so what's the problem? The problem is the one that we have seen before. Is someone releasing an object, let's say a rock, from the top of the building. Okay, so here you go. Here's the top of the building, a height h. Building at height h. Okay. Move this guy right in here. X and Y axis. Okay, and let's see what we want to do. You're at the top of a building of height h. You release a small stone from rest from the top of this building. What's the final velocity of the stone just before impacting the ground? Okay? Using arguments of conservation of energy, ignore air resistance. And okay, so we go ahead and the solution, we refer to the work kinetic energy theorem. Here you go, that's the work kinetic energy theorem, right? Work done by the conservative force, there's just one conservative force in there, which is the weight, plus the work done by non-conservative force is equal to the difference in kinetic energy. Final kinetic energy minus initial kinetic energy. We want to find out the final velocity of the stone. And the final kinetic energy depends on the final velocity. So the final velocity is implicit right in here inside, right? So let's rewrite that. Here you go. Here you go, half mv square. Here is half m p naught square. That's there is no ignore air resistance. Okay, since there is no air resistance, comma, it means that there is. It means that W and C, the work done by a non-conservative force, must be equal to 0. Okay? I place that with this one right in here. And my equation simplifies to something like that. I'm going boldface what I want to calculate. I want to find the final velocity. The initial velocity is 0. So consequently, because the initial velocity is 0, 0, comma, the second term on the right-hand side, cancels. Right? And now we are left with this one right here. Okay? This one right in here. But let's not forget the work done by the conservative force must be the work done by the weight. Okay, the work done by the weight. I put it mg here. And going back here to my, I don't need that, my drawing. Okay. The work, oops, let's see. Yeah, I need the delta R. I need the delta R. Note, see that the displacement goes from the top to the bottom, right? So the work done by the weight is going to be a positive work. mg delta y or mgh. Okay? Make sense? So work done by the weight is going to be given by mgh. And now we have, we don't need to know the mass of the object to solve this problem because the mass is going to cancel. I didn't tell you what the mass is, but I told you what the height is. We have this equation right here. M cancels out with M. And we end up having this final result, which matches the result that we would get if we were using kinematics. Okay? That's one way to solve this problem using the work kinetic energy theorem. A more straightforward way to solve this problem would be just to use the conservation of energy. Okay? Arguments of conservation of energy. Using a more straightforward way to solve this problem is to use arguments of conservation of energy. Okay? So how do we do that? Instead of using the work kinetic energy theorem, we just go back to the argument of conservation of energy, right? We go final potential energy plus final kinetic energy is equal to initial potential energy plus initial kinetic energy. This equation that you see right in here is a consequence of this one that you see right in here. Okay? Since there is no since the work done by the non-conservative force is zero, we do have conservation of energy. So this equation here holds. Okay? Since energy is conserved, here you go, mechanical energy is conserved. Because we are neglecting air friction. Okay? And when we, and how do we do that? We go final potential energy. Go back here, right here. Right? Remember that the equation for the potential energy, what it is, right? The equation for potential energy is mgy, height of the object. Okay, the final potential energy is here at is going to be the potential energy here at the bottom of the building. At the bottom of the building, the height is zero, right? So the final potential energy must be equal to zero because y equal to zero at the bottom of the building. That's another way. Okay. I'm going to change this thing here. Let's do this way here. since at the bottom of the building, y is equal to 0, right? P the final potential energy will also be 0, like that. And then we have to worry about the initial potential energy. The initial potential energy, just like before, is going to be mgh, mgy, right? Where y is equal to h. So we substitute everything out there, right? So let's repeat that here. Here is going to be 0. So we have, I'm just repeating the same thing in a different way, right? Final potential energy is 0. Initial kinetic energy is 0. Final kinetic energy is unknown. We do not know the mass, we do not know the final velocity, and initial potential energy is mgh. Right? And then we end up getting exactly the same result as you got before. As expected, right? We have something like that. Now you choose whichever you think is more convenient. Use just argument of conservation of energy, which is a simpler formula to memorize, or you use the work kinetic energy theorem, right? But don't forget, this equation here is more genetic, it's more general, it's more powerful, because it tells things that this equation here does not tell you, even though this one is simpler, right? This equation here tells things that the other one doesn't tell you. We can even here write that in the following way. Okay, like that, minus final potential. Let's see. Yeah, minus final potential energy plus initial potential energy, like that. Okay, that's what W of C is all about. It's minus the change in potential energy, like that. Oh, delta. Minus the change in potential energy. Like that. And we have a negative sign here. Okay. Let's see how I'm gonna do it. No, I'm not gonna do like that. I'm gonna do like that. Yeah. Like that. It's better. Work of the conservative force. Like that. Okay. And I can even elaborate a little bit more to leave it, similar to the, I can pass the speed to the other side. You're going to sum the final kinetic energy with the potential energy, and we can pass this one to the other side. It's going to add the kinetic energy, the initial kinetic energy, to the initial potential energy. Okay? And I can erase something like that, no? See, here we have the terms for conservation of mechanical energy. And here's the term for the non-conservative force, in case we have a non-conservative force. Okay, that's an example, that's a simple example. We can do also another example of elastic force. Let's take a look here. Example 2. Elastic force, a metal plate is attached to a spring of constant K. An object of mass M is compressed against the plate and displaces the spring by an amount x naught. you release the mass from rest. What's the velocity of the mass at the position of equilibrium when the mass loses contact with the plate, right? Let's see if I have I'm going to illustrate the situation. I can use this one right in here. I compress the spring. Okay. The displacement here is going to be x naught. We're going to have this conservative force, which is the conservative force of the spring. Release the mass. The mass is going to go gain velocity. I'm going to, let's do the movie, right? Compress the spring. And I'm going to illustrate my plate here as well. This plate is attached to the spring. Okay, let's keep it like it's right in here. Spring. If this plate too, yeah, let's put it this way. Plate. I'm going to shorten this plate a little bit. The mass is just making contact with the plate. The plate is attached to the spring. We release it. And what's going to happen? This spring is going to release is going to propel the mass to the right. Let's stretch the spring. At this point right in here, there will be initial velocity is equal to 0, okay? There will be a velocity. I'm gonna put it in black color. Okay. And the mass is going to lose contact with the plate. And it's going to keep on moving to the right. Okay. Going to keep on moving to the right. Assuming that there is no friction, we don't need that. We don't need that. At this point here, since the mass is at the equilibrium position, there is no force, right? I'm going to start right here. Start right in here. I gotta write down that the velocity is 0. Initial velocity is 0. We have this final velocity right in here. And the mass keep on moving on its own because it lost contact with the plate. The mass is not attached to the plate. The mass is just touching the plate, right? So the initial condition is this one right in here. The spring has some potential energy. The final condition, the final situation is this one right in here. The spring lost its potential energy because it's in the equilibrium position. And the mass now has some kinetic energy, okay? Neglect friction and the other non-conservative forces. Let's copy that. Here we go, going back here. Gotta visualize the problem. Okay, already. A metal plate is attached to a spring of constant K. I'm just repeating that, right? An object of mass M is compressed against this plate, not attached, and displays the spring by an amount x naught. You release the mass from rest. What's the velocity of the mass? at the position of equilibrium when the mass loses contact with the plates, neglect friction and other non-conservative forces. Because we are neglecting non-conservative forces and friction, right? Friction being one of the non-conservative forces, we can use argument of conservation of energy, potential energy, final potential energy plus final kinetic energy is equal to initial potential energy plus initial kinetic energy. Okay, so the potential energy that we're talking about is the potential energy of the spring given by kx square. This x should be the final position of the mass. Okay, here you go. Half the kinetic energy is half mv square. Initial potential energy is half kx naught square, initial position, and initial kinetic energy is half of mv naught square, like that. Okay? As I mentioned before, the final position of the mass is going to be at x equal to 0, right? Take a look here. I put my x coordinate system. The origin of my x coordinate system is exactly at the position of equilibrium. So this one is going to be 0. The initial velocity is 0. Consequently, the initial kinetic energy is going to be 0. And now we have the solution here. We want to find, I'm going to emphasize that I want to find the velocity, the final velocity. We go, we don't need that. We don't need that. Step by step, half cancels with half. And then divide both sides by m. Okay, and we have that solution right in here. X not only equal. That was going to be the final velocity. Okay. We can do another example now based on the potential energy of the due to the universal gravitational law. Okay. A spin launch launcher. Have you ever heard of this spin launch device? Okay. Let's take a look. They have it. They have this crazy technology that they developed in the States. The crazy ideas are the best one. And I'll never imagine that they would, it makes sense what they try to do, but I never imagined they would implement anything like that. Let's take a look at the Wikipedia, right? Wikipedia is better. Here you go. Spin launch. It's a spaceflight technology development company working on mass accelerator technology to move payloads through space. Instead of put fuels in your rocket, right? You just slingshot a payload into space. Here's the history of the company, spin launch. The technology, let's take a look at the, they don't have what a shame. They don't have a picture, but we can go to the company's website. Here you go. One of 100 most influential companies of 2022. Look what they do. You know, here you go. The space launch system. They put to rotate, and that's their facility, right? Okay, that's how they do it. Here, do you see the rocket, the projectile? they spin the projectile inside a huge centrifuge. They go faster and faster. Oh, here you go. That's the device. Oh man. And here you go. Here's the projectile coming out, right? At a very high speeds. Let's see if we can have a better video so you can understand. And let's see. Okay, here is the centrifuge that I'm talking about. They have vacuum inside the centrifuge. The payload, the rocket, gets out from this barrel right here. A new way to get to space. And here, you accelerate fast enough. Should be accelerating in this direction, in the counterclockwise direction. Okay. And when it reaches the right speed, they release the projectile from this barrel that you see right here. It's an innovative new technology company that has created an alternative method of putting 200-kilogram class satellite into low Earth orbit. There are very high acceleration levels right here. Humans couldn't be launched from this facility. Okay, you need to launch only inanimate objects. Otherwise, a human would die at the high acceleration levels here. Let's see. Unlike traditional fuel-based rockets, spin launch uses a ground-based electric-powered kinetic launch system that delivers substantially less expensive and environmentally sustainable approach to space access. Okay. Now here's the centrifuge in the vertical direction. Unfortunately, yeah, here you go. Here's the payload. Orbital, suborbital, orbital as well. Suborbital is easier than orbital. Okay, here you go. That's the suborbital accelerator. Let's take a look. You have already seen that, right? Let's see. Let's play it anyway. Spaceport America. That's the desert. You cannot launch something like that from populated areas. If the axis of rotation, we go. 7, 6, 5, 4, 3, 2, 1, fire. Whoa! That's in slow motion, right? They impart a rotation to the rocket so it stays oriented in the proper direction. Oh my God, it's so funny. There you go. Okay, so that's the spin launch technology device. Let's see where those guys are located. Let's see. I think contact. Long Beach. Ha ha ha. Okay, so it's next door to LA Harbor, right? Long Beach, California. That's their phone number if you want to contact them. But I want to know, of course, they don't launch it from Long Beach. They have to go to the desert to launch that stuff. But that's their headquarters. Okay. So let's go back to our example, right? A spin launcher propels a payload at very high speed v along the vertical direction. Find the maximum height this projectile can achieve using arguments of conservation of energy. Consider that the height is high enough, so you have to use the universal law of gravitation. Neglect air friction. Okay, that wouldn't be when you launch those things from their surface. You must you must account for air friction. But just to make the problem simpler, okay? Air friction is not negligible. But just to make the problem simpler for you, we are, neglecting air friction and other non-conservative forces, okay? Radius of Earth is r and its mass is m, okay? Okay, so we go ahead and use find the maximum height this project can achieve, okay? So we know the velocity, so we are going to use conservation of energy. Final kinetic energy plus final potential energy is equal to initial kinetic energy, initial potential energy. And I'm going to illustrate the situation here. More students coming. Very important to make a drawing of the situation every time that you solve a problem. A picture is worth 1,000 words, right? Imagine writing 1,000 words right in here. You would take forever to do that. That's why we use pictures. We use pictures to save on time. Here you go. Here's the Earth. I'm gonna get this guy here. We're not using, remember, we are using universal law of gravitation, right? Radius r. You cannot use mg in this case. You have to use the other equation. Here you go. Radius of the Earth for r. And the way it goes is like that. Here you go. Here's my projectile. It's being launched in the vertical direction. My right, right? Here you go. I'm gonna make it a spherical one. And it's being launched upwards. I'm gonna put it like that. Okay, that's the velocity is given. Did I give you the mass as well? I don't need the mass. You don't need the mass for that. Unless you account for frictional forces. And what do you want to know? You want to know the highest height that this projectile achieves. Okay, and the highest height is achieved whenever the velocity is equal to 0. Like that. Final velocity. I'm going to even put it here, initial velocity. So there is no doubt about that. Subscript. Okay. Let's put a vector like that. Initial velocity. Final velocity. As time goes by, the project climbs into space and its speeds decrease, right? If you want to play the movie, you can play like that. You go, this guy, little by little, the arrow decreases in size, right? Velocity instead of v naught, now let's say it's going to be v1. Playing the movie. Next frame of my movie is going to be like that. Climb into space. The arrow of the velocity shortens. And that's going to be v2, right? Until it reaches v final, okay? V naught, v1, v2, v final. right? So we go ahead. That's going to be my initial kinetic energy plus initial potential energy. So initial, let's work this one here. Initial kinetic energy is going to be half m v naught square. Initial potential energy, now we have to use that equation, right? That I explained to you, right? It's going to be minus the other one, big G, big M, which is the mass of the Earth, is now, mass of the payload, small m, divided by the distance of the small mass from the center of the Earth. Okay, it has a negative sign. There's a negative sign here. Okay. Final potential energy is going to be 0. And then we are going to have a final potential and a final kinetic energy is going to be 0. And then we're going to have a final potential energy. Let's go see there. You go right here. And I have to write down that this is a height, right? H. Like that. H. Whoops. Right here. But don't forget, this equation applies, the equation for the potential energy applies for the distances from the center of the Earth. It's not from the Earth's surface. That's the important difference between one equation for the potential energy, gravitational potential energy, and the gravitational potential energy, and the other for the gravitational potential energy, okay? So here you go. That's gonna be, I'm gonna copy and paste right in here because it's gonna be exactly the same thing. But instead of just R, it's gonna be R plus H. And by the way, this R here is gonna be uppercase R, which is the radius of the Earth. Okay? We want to know this guy right here. What's the height? Given the velocity, the initial velocity. I'm gonna put down V naught here. So there is no doubt about that. This 0 disappear. This mass cancels out. M, M, and M. Here's the mass of the Earth. Okay. Here's the radius of the Earth. That's documented in any book. And I want to solve for H. Mathematically, it's going to be a little bit challenging. Oh. Huh. Yeah, okay, good. Work it. Right, I'm going to let's see, I'm going to pass G downstairs. So we got rid of this one. I'm going to pass big M downstairs. Big M downstairs. Here going to be G and big M as well. Right? So we have that. Let's see, can we simplify anything? The second term we'll be able to simplify the second term. G cancels with G. M cancels with M. 1 over that. All right, so I can, that's the negative sign, we have to put the negative side on the other side, right? Negative here, positive here. take the inverse of everything, both sides. And what do we get? Here we go. Might be better put under the same denominator, right? I should have put under the same denominator from the very beginning. This one is going to be, first I'm going to put between parentheses, right? Here you go. Power of -1, like that. And now I can start putting that under the same denominator. Hopefully it's going to simplify our equation. I gotta divide by r and multiply by r. I gotta divide by 2gm and multiply by 2gm. Now we have the same common denominator. I'm going to commute those two so I don't keep on carrying an additional plus sign. Let's see if we fit it here. 2gm minus r v naught square. Right? Here you go. There's a reason why I put under the same denominator, okay? So I can put in a better format, the final result in a better format. Erase all the stuff. Okay, and now just invert whatever is downstairs comes upstairs, right? You want to even put outside this guy here. And whatever is right here, I put it right in here. The problem is almost over. And is the height that we want to know. Radius of the Earth must go to the other side. Okay, can we do better than that? Yeah, doesn't look like. Maybe, let's see. Maybe we can do like that, 2gm divided by 2gm divided by 2gm, right? If we do something like that, this one becomes 1. That's the best we can do. We cannot do more than that. Okay. Might be even better keeping this like that. Oops. Here you go. Like that. GMR. Okay. So 3 different examples. 3 different examples. One for the regular force of gravity nearby the Earth's surface. The other for the spring constant, for the elastic force, and the other one for the force of gravity using the universal law of gravitation. Here you go. I'm adjusting my clock here. 9:43. And then, I want you to do homework by yourself, okay? There's a very interesting one here. Find h. for the following initial velocities. If the initial velocity is 7 kilometers per second, what's going to be h? In the vertical direction, right? If the initial velocity is 9 kilometers per second, what would be h? If the initial velocity is 11 kilometers per second, what would be h? Do that at home using Excel or using your calculator, whatever you think is best. Okay? Maybe not. So we have covered everything but power. I even provide you with examples, right? So I think that's a good point to take a break. And before we take a break, let us get attendance, take attendance, roster. Here you go. Lecture. 11 was a holiday, right? And today is the 18th. Chat. Let's start with Audrey. Are you there, Audrey? Audrey Aguilar, I don't see Audrey. Brianna Carrillo. Are you there, Brianna? Yeah, okay, thank you. Jazzy. Thank you. Gabriel Contreras. Gabriel disappeared, huh? Let's see, Liliana Cortez. I don't see Liliana here. Molly. Thank you, Molly. Henry Kim. Oh, I don't see Henry here. Next is Ruth. Hello, Ruth. Ruth not here. Noemi Martinez. Thank you. Danae Miller. Thank you. Ramon Olivares.
Here.
Thank you. Taylor Thorne.
Here.
Thank you. Stephanie Ramos.
Here.
Thank you, Stephanie. Next is Jeremiah. Thank you, Jeremiah. Sean Rosario. Thank you, Sean. Ali Standard. I don't see Ali here. Jason Strait.
Here.
Thank you, Jason. Elena Trujillo. Let's see, I saw Elena checking in, right? Hi, Elena. Must be away from her computer. Let's see. Another student coming in. Let's see, who is that? Henry. Jason Valadares.
Here.
Thank you, Jason. Next is going to be Larell Williams. Thank you, Larell. Nuhamin. Nuhamin Wanhu. I don't see Nuhamin in my roster here. Alia. Alia Zavala. Okay, I can see Alia in my roster, but I don't. Let's see, Henry Kim. Are you there, Henry? You just joined us, right? Henry is not replying. Okay, so let's see. We have 3 students who didn't reply. 13 plus 3 is 16. Okay, matches. 9:50 right now. Let's take our break. from 9:50 to 10:05 a.m., right? Any questions? Oh, Henry, okay, thank you, Henry. Henry, right here. Now I want to give up an opportunity for Elena. Elena, are you there?
Yeah, I'm here.
Okay, thank you. And Aliyah? Aliyah must be away from her computer. Okay.
I'm here.
Oh, you're there? Okay, thank you. 16, good. So let's go for our break, and we're back at 10:05. Okay. See you soon. Okay, share the screen. Okay, and finally, the last thing in this chapter is going to be power. I'm just going to copy and paste all the chapters, all the sections of this chapter. We didn't cover this one, you're not going to cover. Although it's nice that you know that there are other forms of energy. Okay, and so let's talk about power. Right? Last thing is power. We talk about the idea of work. And I want to give you an idea what power is, what's the difference between power and work. Very important, okay? So I'm going to give you a practical example. Suppose that you are in the market to buy a crane. You want to lift a very heavy load, 1,000 kilograms, which is the mass of your car, most cars out there, to a height of 10 meters. Okay, so the energy required to lift a load of 1,000 kilograms to a height of 10 meters is going to be 10,000 joules. And then you ask the salesman if he has a specific about the crane, right? And he asks the salesman, about the device. He goes about the crane that can do this type of work, and the salesman said, "Oh yeah, we do have a crane. Okay, it can lift this. It can do work on this amount, 10,000 joules, and the price for this crane is $10,000, right? $10,000 should be like $1 per joule. Okay. Then you're shopping. You want to know whether you can get a better deal elsewhere. You still didn't decide whether you're going to buy it or not. Then you go to another store, and the second salesman tells you that he also has a crane that can do the same amount of work for half the price. Okay? So we're talking about here now you're paying 50 cents per joule. Okay? So the question is, would you buy the cheapest crane right away? Or you do some more research to find out why the other crane is cheaper than the other one, right? Why one crane is cheaper than the other one? Okay. Most likely, the difference between those cranes has to do not with the amount of work that each crane can do, but it has to do with the power, with their power. Okay, most likely. That's why one is more expensive than the other. Okay, the difference between these two cranes, most likely, the difference in price between these two cranes has to do with something that we call power. Both cranes can perform the same job of lifting the same load 10 meters high. However, at this point, you have to stop and ask the salesman, The two salesmen, right? The two salesmen. What's the power of each crane is, or how fast can each crane do the same amount of work? Okay, that's what you have to ask, and then you can finally make a decision. What's the power of each crane? Right? Maybe the crane that is more expensive, maybe it can do the same amount of work in half the time, right? Maybe the more expensive crane can do the same amount of work in half the time. Have you thought about that? Right? That's what power is all about. So power is how fast you can perform a given amount of work. For example, you know, you got first crane, the first crane can perform the first job in 10 minutes. But the second crane, because it's cheaper, most likely it will perform the same amount of work in a much longer time, 20 or 30 minutes, right? Okay, let's put here 20 minutes in 20. Okay, what is the power? What is the power of each one? Okay. And the equation for the power is, I'll write that down here for you. Here's the equation for the power. Amount of work divided by amount of time. And we can start playing with numbers. Solution. But the second crane, because it's cheaper, will perform the same amount of work in 20 minutes, right? What's the power of each crane? Like that. Okay, so we are talking about 10,000 joules. Here we go, P1. P1, right? This is going to be delta W divided by delta T1. The amount of work is going to be the same, right? It's just the amount of time that's changing. You know, P2 is going to be like that. And then we can start trunking some numbers here. We go, the amount of work is 10,000 joules, 1, 2, 3 joules. And the amount of time, I said it's 10 minutes times 60 seconds. Times 60 seconds. The other one is going to be not 10 minutes, but 20 minutes times 60 seconds. Now you do the math, right? It's going to be 10,000 joules divided by 600 seconds. The other one is going to be 10,000 joules divided by 1,200 seconds. And the unit of power is going to be joules per second. And joules per second is something that happens so frequently in physics that we give it a name. We call it watts. Okay. So I'm going to do the math here for you. The first one has a power of 10,000. 1, 2, 3 divided by 600. 16 plus 0.66. 16.67 joules per second, which is equal to 16 plus 67 watts. The other one is going to be half, right? Half as much. 8.33 watts. So if your time for you is important, you might want to buy the more expensive crane. Okay, so that's the very bare idea of power, how fast you can do a given amount of work. Okay, here's the unit of power. Okay, W, delta W over delta T, watts or W. And there's another way of writing down this equation of power. Okay, just to go back to our definition here of power. Amount of work divided by amount of time. Another way of writing the equation for power. Here you go. We start with the very definition, right? So let's not forget that the amount of work. We saw that the amount of work is going to be the force times displacement, right? Remember that? Here we are assuming that the force is constant throughout. Oh. Okay. If the force is constant throughout, we can display the equation just like that. And recognize that what you have right in here is nothing plus but the velocity. Force times velocity also is another equation for the power. Okay. And that's what we have for chapter that's what we have for chapter 6. Energy, work and energy. Work and energy. Any questions about that before we move into chapter 7? We're done with chapter 6. Let's take a look at the book. Wiley plus. Wiley force resources. Launch. Work and energy. Chapter 6. Right? There you go. Power. Here is the power of a human body, right? Whenever you're running, the power of the human body whenever it's running is 1340 watts, skiing, biking, walking, and sleeping. You still spend energy whenever you're sleeping, okay? You still spend some energy. You even lose weight whenever you are sleeping. You lose roughly 2 pounds per 8 hours of sleep, roughly. Because you have all this machinery inside your body that's doing some work in there. And okay, and now the next one is this one, impulse and momentum. Okay, I usually skip impulse. I usually skip impulse momentum theorem. And here go the chapter 7. Okay, here you go, chapter 7, linear momentum. I hate when he does that. There must be a way of learning. Oh my goodness. Let's see, 7.1. Yeah, okay. 7.2. 7.3. 7.4. And 7.5. Okay. So we are going to concentrate on those three sections. Principle of conservation of linear momentum, collision in one dimension, collision in two dimensions. Okay, what you have to know about linear momentum is a very useful quantity, and it is closely related to Newton's second and third laws. Okay, keep in mind, momentum, conservation of momentum is a consequence of Newton's, actually first and third laws of motion, not second, but first law of motion, first and third laws of motion. Okay, so it's gonna look just like that. Remember Newton's, it should be, first, let's put slash second, right? Because first law of motion has to do with the second as well. First slash second and third laws of motion. Okay, second law of motion states that the net force applied to an object, to a mass, is going to be the mass times acceleration. Okay, which is mass delta V over delta T. Okay. And we can go ahead and say, I'm going to explain like that. Delta V is going to be final velocity minus initial velocity, right? That's what it is, right? And look what's going to have here. I'm going to distribute my mass on those two velocities. And so we get this relationship that's something like that. Okay? Momentum is closely related. We can even say that the idea of conservation of momentum is a consequence of Newton's first and third laws. Okay, and let me show you. Okay, so if the net force is equal to 0, something interesting happened to this equation. If the net force is equal to 0, right, something interesting happened to the above relation. Think about that. Yeah. if the net force is equal to 0, now we are talking about Newton's first law of motion, right? But let's see what else happens to my equation here. If the net force is equal to 0. If the net force is equal to 0, okay, let's keep it my net force equal to 0 here. This also implies that this quantity that you're going to have here upstairs is also going to be equal to 0. Do you agree with that? Right? But even better, not only this equation here, this quantity is going to be equal to 0, you also have that the mass times the final velocity is going to be equal to the mass times the initial velocity. Okay? That's the very idea of conservation of momentum, of conservation of anything, right? Recall what I told you before, right? What I told you before, okay? If something at the beginning is equal to something at the end, comma, it means that this something is conserved, okay? And this quantity that you see right here, mv, is one of those quantities that get conserved when the net force is equal to 0. Okay? The above quantity, m times v, mv, comma, we call momentum and represent by the letter p. Okay? So here you go. P is lowercase p equal to mv lowercase p naught is equal to mv naught. Okay? And there is a very good reason why we define this quantity. There will be some very important situations in which the momentum will be automatically conserved. Okay? That's when Newton's third law of motion comes into play. And I'm going to explain here with an illustration. Let's go back to my illustrations right here. This one. Let me illustrate. You can best realize the importance of this quantity when you look at the slides that I'm going to show you. And my slides start right in here. Right, here we go. All illustrations. And here you go. 0.8 momentum. I'm going to even specify linear momentum. There's a reason why I specify linear momentum. Because there are other types of momentum. Okay? Let us say, okay, here you go. Linear momentum. Okay, here you go. Consider the fact that we have this object that's going to collide with another object that is at rest. Okay, consider that. Okay, when this object comes, just before it collides, here, consider that there is no friction, frictionless surface, linear momentum, frictionless surface. At the very moment of the collision, what's going to happen? Those two objects are going to get into contact with each other, right? And what's going to happen? Object number one is going to exert a force on object number two to the right. And according to Newton's third law of motion, there will be an opposite force applied to object number one, right? Here you go. Force of one applied in two, force of two applied in one. Okay? And what did I put around this object number one? There's a reason why I put this square around this rectangle around object number one, okay? I put this rectangle around object number one to emphasize that our system is going to be just this object, nothing else. Okay? So here you go. My system. Between this instant and this instant right in here, my system is subjected to a net force equal to zero because it's sliding over a frictionless surface. Okay? So between this instant, t equal to zero, and this other instant, just before the collision, we did have conservation of linear momentum on object number one, right? But the moment that we have the collision, we do not have conservation of momentum anymore because there is this force being acted on object number one. Okay? Think about that. So let's write that down here. Now, let us see, right? Let us see how we can apply this concept to collisions, to a collision between two objects, okay? Two objects of same mass, one at rest and the other moving towards the first one. And that's what we have right here. Initially, consider that we will focus only on the moving object as being my system, okay? We're going to ignore the other one. My system is going to be just the first one. At time, at time t equal to zero, mass one, let's see how we can apply this concept between two objects of same mass. One at rest and the other moving towards the first one. Okay, one at rest, object number one. Let's see how I did that in my drawings here. Oh yeah, okay. I'm gonna keep okay, one moving with constant velocity, okay? Object number one. I want to be consistent with my drawing. And the other at rest, object number two. Initially, consider that we will focus only on the moving object as being my system. At time t equal to 0, object 1, is moving with an initial velocity V01, like that. And the second, whereas the second object has an initial velocity V02, okay? Not for initial, 2 for the object, number of the object equal to 0. It's at rest. Okay. What can we tell? What can the surface? Assume the surface is frictionless. Frictionless, right? Between t equal to 0 and just before the collision of the two objects, comma, the force applied to one is 0, right? In other words, we just before the collision, let's call it T1. The total force applied to one is 0. In other words, we do have conservation of linear momentum for object number 1 alone within the following time interval: 0 less t less t1. Like that. Like that. Okay. However, exactly at T1, object number 1 feels a force due to 2, right? And after that, we cannot say that its momentum is conserved, right? So let's play the movie again so you understand what's going on. Here you go. Object number 1, moving towards object number 2. From here, at t equal to 0 to here, t equal to t1, momentum for object number 1 is conserved because the surface is frictionless. Net force applied to this object is 0. But the moment there is a contact with the second object, we can no longer say that momentum is conserved, right? Momentum is no longer conserved between this instant and soon after the collision, because net force is no longer 0, right? Well, that's one way of looking at this situation. There is a smarter way of looking at it, okay? There is a smarter way of looking at it. Here, I'm considering object number 1 as being a single, as being my system, okay? And I'm gonna write that down here. Mass 1 is our system. What if we start thinking in a different way? What if we start considering not mass 1 being our system alone, but what if What if masses 1 and 2 are together our system? And then put a question mark right in here. The situation becomes very interesting. Okay? Here you go. Now, did you notice that I put a box, a rectangular box around the two masses? Okay? Here, I'm treating those two masses as though as they were a single one. I'm treating those two masses as though they are our system. Okay? And it is like an object that can stretch and contract, right? At this moment in time, the object is stretched. At this moment in time, the object is contracted, the system is contracted. At this moment in time, the two masses are interacting with each other. But then there is something important here. There is something very important here. The net force applied to the system, the net force applied to this net mass 1 and 2, is going to be 0 in view of Newton's second law, in view of Newton's third law. Recall that third law says that when two objects interact, the force of one applied on two is going to be equal in magnitude and opposite in direction, right? So if they're equal in magnitude and opposite in direction, when those two forces are summed up, you're going to have a net force is equal to 0. And that's the neat thing about collisions. That's the neat thing about collisions. We can treat collisions between two objects as though the two objects were a single one. And because now they're being treated as a single one, the net force applied to this system, to these two objects, is going to be 0, and momentum will be conserved. Okay? That's the neat thing about choosing your proper system. Choosing your system in a proper way, okay? Let's write that down. Here you go. However, exactly. Okay. As you can see from the above, conservation of momentum before and after a collision, cannot occur if my system is just one of the objects. Okay. However, if you choose your system as being the two objects simultaneously, the situation changes considerably. And that's a real nice trick that we discovered some time ago. Okay? Changes considerably. Note that at the moment of collision, the net force applied to our system is going to be 0 by virtue of Newton's third law of motion. Okay? So the situation is going to be like that, right? Here you go. Initially at t equal to 0, right? We're going to play the movie here in words, the script of our movie. Initially at t equal to 0. one of the object one, which by the way, which is part of our system that encompasses objects 1 and 2 simultaneously, 1 and 2 simultaneously, is moving simultaneously. Here you go. Is moving, is subjected to a net force equal to 0 because it is moving with constant velocity, comma, at t equal to t1, just before the collision, linear momentum is still conserved because object 1 is moving with constant velocity over a frictionless surface, right? At the moment of collision, and at the moment of collision is at t equal to t2, at t equal to t2, okay? Object 1 exerts a force F of 1 and 2, right? Let's make sure that we are F of 1 and 2, yeah. Exerts a force in 2, exerts a force into F1, 2, force of 1 and 2, and in view of Newton's third law, F of 1 and 2 is going to be equal to minus F of 2 in 1, right? And this one is supposed to be a vector, okay? So at t equal to t2, comma, the net force applied to our system composed of objects 1 and 2, objects 1 and 2 will be 0. Or, or F of 1 in 2 plus F of 2 in 1, right? Plus F of 2 in 1 is equal to 0 because of the third law. Consequently, momentum of this system must be conserved before and after the collision. Okay? That's the important conclusion that we must have. So now we are going to come up with an example. Okay? Example. Consider a inelastic collision between two masses, two objects of same mass m. The first object is moving. The first object has a non-velocity. The first object has a non-velocity, v01. And the second object is at rest. Find the velocities of both objects after the collision. You got the collision. And by the way, what means inelastic collision? Inelastic collision is a collision by which both objects stick to each other. Okay? That's what inelastic collision is all about. Here you go. And it is illustrated right in here. Okay? Before the collision, the objects are separated. After the collision, they are glued to each other. It's possible to duplicate this type of collision. This type of collision is called inelastic, and it is very important, this type of collision. Okay? You can, you may duplicate an inelastic collision in real life, an inelastic collision in real life by attaching a Velcro, a piece of Velcro in each object, right? So if you put a piece of Velcro here on this one, on those two objects, they're going to stick to each other once they collide, right? So that's what I want to do. You want to find out the final velocity after the collision, after I did inelastic collision between two objects of same mass. Between two objects of same mass. Okay, so here we go. Solution. The surface. Assume the surface. The two in contact with the two objects is frictionless. Okay. So here you go. First, what do we know? Net force is 0. Consequently, initial momentum must be equal to final momentum, right? But when we are talking about the momenta here, we're talking about the net momentum. Initial momentum means what? Mass of 1 times, I'm doing that vectorially, okay? Initial velocity of 1 plus mass of 2 times initial velocity of 2. That's what I mean by initial momentum. And I also, what do you mean by final momentum? I'm doing just a step by step here. The same thing. Initial mass of 1 times final velocity of 1 plus mass of 2, final velocity of 2. That's what I mean by net momentum. Okay? Initial momentum must be equal to final momentum. According to this problem, the second object, the masses are the same, right? Because the masses are the same, M1 is going to be equal to M2, which is going to be equal to M. So, since the masses are the same, we can write something like that. Here you go. Like that. Right? What else? We know that the initial velocity of the second object is 0. Initial velocity of second object is 0. Then we can simplify the first equation. Here you go. This one here is going to be 0. Right? And then there is one more important piece of information that I told you. Since the collision is inelastic, okay? What can we tell about collision being inelastic? It means that the final velocity of 1 must be equal to the final velocity of 2, right? Which, by the way, I'm going to simplify just with the v vector, okay? Like that. V vector like that. And now we can apply this third condition, 3 different conditions, right? Given by the problem. Masses are the same, second object is at rest, and then the collision is inelastic. Since the collision is inelastic, the final velocity here of both objects will be the same. Okay. I do not know what the final velocity is because the momenta are the same for both objects. Then we are going to have 2mv vector like that. I can erase my 0 from here. And now I can apply conservation of linear momentum. Applying linear momentum conservation. We have, I'm going to use this one here, right? And then I will copy this one, paste right here, copy this other, paste right in here. All right? And now we can solve our problem. M is going to cancel with M. And the final velocity ends up being equal to, well, what did I do here? Yeah, okay, here you go. Like that. Final velocity, V01. V01 ends up being half the speed. V final one ends up being half the speed of the initial speed. Okay? That's what we get when we have this type of situation. So I'm just going to copy and paste what I wrote in my previous note that I think it's is better written than what I did so far. Okay. Okay, so here you go. Examples of conservation of momentum, right? A single object moving over a frictionless surface. Net force is 0 and the velocity is constant, so the initial momentum. I didn't illustrate that, but it can be. Let's see if I have it here. Yeah, I don't have an illustration for that. But from here to here, right, is the illustration of a single object moving with constant velocity over a frictionless surface. And because of that, momentum for this object alone, the first one, would be considered conserved. Okay? And then we have this not so obvious case, a system of two objects which are colliding. Momentum is conserved just before the collision, and at t, just after the collision. Momentum is conserved for the following reasons. During the collision, object 1 is interacting with object 2, interacts with object 2. More specifically, object 1 is applying a force F12 to object 2. Conversely, and according to Newton's third law of motion, object 2 must apply a force F1 minus F12, right? Consequently, the net force in the system must be 0, comma, must be 0 because of Newton's third law. Just a little bit. I'm just, repeating what I told you before, but in a more organized way, in a more compact fashion, organized fashion, right? So let's see, do we have any questions so far? 11 o'clock right now. Let's take a break. Break. 11:02. Let's do 11:02 a.m. to 11:17 a.m. So if you don't have any questions, let's have our break now, and I will see you in 15 minutes. Okay, so now we're going to come up with another example here. We did example one. Example one dealt with two masses, two objects of same mass, one moving and the other at rest. Okay, and we can have all sorts of examples. Okay, this is the simplest type of example. This is the simplest example you may have. You may end up solving. There are more difficult ones, okay? And by the way, this is a 1D collision problem. One-dimension collision problem. One mass at rest. That's what it is. But we can come up with a different one. Let's, here you go. That's what example 2 is all about. Okay, so here you go. 1D inelastic collision. Two objects of different masses, M1 and M2. The masses are known, okay? V02 is equal to 0. Find their final velocity. Consider the surface to be frictionless. Okay, find their final velocity or speed, right? Can be speed as well. So let's illustrate the situation. Let me close this one. This one here. Go. Okay, something similar. Let's see. That's M1 equal to M2. Let me see if I have M1 greater than M2 here. Oh yeah, here you go. M1 greater than M2. Two objects. One at rest, the other moving towards it. They collide. Okay. And in this case, okay, this case is not inelastic. Okay. Okay, this case is not inelastic. This is elastic. But in inelastic collision, let me, I'm going to, oh, you have a picture. Let's see here. It's going to be just like this one. But the only difference here is going to be just like this one. The only difference being that the object, the first object is going to be larger, right? There you go. 3 times the mass of the other, okay? That's the only difference here. Bring to front. I'm going to expand my box. Okay, here's the collision between the two masses. Need to expand my box. They're stuck to each other because it's an inelastic collision. And should be M1, right? M1 subscript, M2. Like that. Right, M1, M2. M1, one is M1, the other is M2. Like that. M1, like that, go. M2. And now we can start. Here you go. Initial momentum, right? Final momentum with a final velocity. Inelastic collision. Again, in order to have an inelastic condition, we can attach a Velcro between those two objects, those two masses. So let's do the step-by-step solution, right? The surface is frictionless. Consequently, the net force must be 0. If the net force is 0, there is conservation of momentum, okay? Net force in the system is 0. Consequently, momentum is conserved. Like that. Initial momentum can be broken down into initial momentum of 1 plus initial momentum of 2. Don't forget, this is a one-dimensional problem. Final momentum can be broken down into final momentum of 1 plus final momentum of 2. Initial momentum of 2 is 0 because it is at rest. Number 2 is at rest. Initially at rest. Because we have an inelastic collision, the final velocity of 1 is going to be equal to the final velocity of 2. Consequence of inelastic collision. Go. And now we can replace this relation right in here into this equation, like that. Right? And then we can find the final velocity. The final velocity of the system is going to be less than the initial velocity of mass number 1. You can see, I can even rewrite in a different way. Okay, write that. If you write like that, you notice that this ratio that you see here is less than 1, right? If this ratio is less than 1, it means that the final velocity is going to be less than v0 1. Okay? Real life examples of inelastic collision. Collision between two objects that have Velcro attached to them. Okay. Collision between two cars. Nowadays, cars are engineered to undergo an inelastic collision to preserve the lives of the passengers. In this case, the frame of the car is wrecked, but the lives of the passengers are spared. Have you ever noticed the newer cars, they get wrecked? Notice that the newer cars, notice that the newer cars get wrecked more easily than the older ones, okay? But this is done to preserve the lives of the passengers. We can come up with another example, which is going to be the opposite of an inelastic collision. And the situation is like that. Two objects of same mass initially stuck together and at rest can, for instance, be a gun and a bullet, for instance. Assume that the gun has the same mass as the bullet. Somehow an internal force is activated, right? It can be gunpowder, for instance. It can be gunpowder, for instance. Whose combustion is triggered. It's triggered. When the two objects fly apart, an explosion. Okay, so here you go. The situation is going to be like the following. Let's see if I have it. Maybe I'll have to. Yeah, I'll have to do from scratch. It's going to be the reverse than what you saw, okay? So okay. Oh, I didn't. Okay. Send to back. Uh-oh. This one is gonna be format shape. Let's see. Fill. Oh my goodness. No, it's not what I want. I want that. Okay, now we have it. Here you go. This is mass 1, right? We no longer have there's a moment of transition, so we cannot say that the not is equal to 2. That's okay, we can put it like that. like that. And then what I want the other one here in reverse. Okay. Two objects of the same mass, but they're not moving, they are at rest. Initial velocity. Initial velocity is equal to 0. Like that. Here is my system, right? The two masses are my system. And then somehow we activate an internal force in the system that pulls the two objects apart. Like that. Go for it. Like that. Yeah. Okay, that pull the two objects apart. Can be a gunpowder exploding. This type of collision, right, is like an explosion. It's a collision in reverse. Okay, and after this force, the two objects move away from each other. Here you go. I want this one right here. On this one first. Copy. Okay, soon after the explosion, that's going to be V final of 1. And then the other one, V final of 2. What's going to be the V final of 2? V final of 2, not necessarily equal to 0. The initial velocity, yes, their initial velocity is going to be equal to 0. V final. They're together, right? And I'm going to separate here with a blank slide so you don't get confused. This one goes right in here. Like that. Okay. Okay, now we can play the movie. Two objects at rest. There is an explosion that pulled the two objects apart. We're gonna have V final of 1, V final of 2, right? And he's gonna be my last slide. The system is stretching. Like that. There you go. Boom, boom. They're moving away. That's the illustration. Now let's solve the problem. This is initial momentum. And this one here is going to be my final momentum. Okay, so let's get it. Momentum is conserved. Net force throughout the whole process is 0. Consequently, momentum must be conserved. Okay, what does it mean momentum must be conserved? It means, you know, since the object is at okay, we do know that the initial momentum is equal to 0 because most masses are at rest. Consequently, the final momentum must also be equal to 0. Moment must also be equal to 0. But let's not forget, final momentum has two components. Final momentum of 1 and final momentum of 2. Oops. Final momentum of 1. Oh, equal to 0. Okay, igual. Mass V final of 1. Mass V final of 2. Okay. We gotta put M in evidence. Like that. M cannot be 0. The only term that must be 0 should be since, M is different of 0, then the other term must be equal to 0. And let's not forget this is still a vector, right? And then what we get? We find that their speeds are going to be the same, right? Like V final of 1 is minus V final of 2. The speeds will be the same, but the directions will be opposite, right? It's gonna be like that. If V final of 1 is equal to minus V final of 2, V final of 2 is equal to minus V final of 1. They have the same speed, okay? The two masses have the same speed because the two objects, right, end up with the same speed because they have the same mass. Okay, that's what we find out. We found the relation between their velocities, but not their actual velocities in terms of known parameters. So there is something missing here. Okay. If you want to know the exact value of the final velocity, if you want to know the exact value of the final velocity, you must know the internal energy or the potential energy of the compounder that propelled the two objects. Okay? In this specific case, think about that. In this specific case, momentum is conserved, but not energy, right? But not mechanical energy. Not kinetic energy. Kinetic energy is not conserved. You go here, they are initially at rest, and suddenly they have some kinetical energy here. That's because there is some internal energy here that's being transformed. This internal energy can be also considered a potential energy. Potential energy of the chemicals that undergo the ignition and propel the two objects apart. Okay, so and then we can, example 4 deals with this problem. Let's say I do know what is the potential energy of the gunpowder, the internal potential energy of the gunpowder. What would be the And what would be the final velocity, okay? Refer to the previous problem and assume that the potential energy of the gunpowder before explosion is U naught, and 100% of this energy is converted to kinetic energy after ignited. Find the final velocity in terms of U naught, okay? So now we have a combination of conservation of momentum and conservation of energy. Momentum before and after is conserved. Energy before and after is conserved. The initial kinetic energy is 0. Consequently, I can put a 0 right here. Once the potential energy of the gunpowder is expended, afterwards there's nothing else left. So the potential energy of gunpowder, the final potential energy of the gunpowder is going to be 0. Okay? And now we can start solving our problem. I'm going to what we have here is a system of equations. Okay? A system of equations. A system with 2 equations. 2 equations because this is a one-dimensional problem, right? I can go the next step. Okay, the kinetic energy is going to be kinetic energy of the final kinetic energy. It's going to be the final kinetic energy of the first object plus the final kinetic energy of the second object. And here, that's how we spell. We found out that the final velocity of 2 is minus the final velocity of 1. We have a negative sign that's going to be raised to the power, and this negative sign is going to be canceled out, right? And then we're going to have half of the same thing, which is this term. Let's do that step by step. So here you go. I'm going to do, like that, right? Let's write it down. And from scratch, half m v final of 1 squared plus half of m final of 2 squared. But from the previous example, I learned that this final of 2 is equal, velocity of final of 2 is equal to minus velocity of final of 1. But let's not forget that this term must be squared. And when this term is squared, the negative sign that you see in there becomes positive, and we have exactly the same parameter, the same equation, right? Now I have half of something plus half of the same thing. Which is reduced to that. Unfortunately, I cannot put there at the stop. Okay, yeah, I can. Here's my U naught. Right? V final of 1 equal to minus V final of 2 comes from this equation right in here. Let you see. And now we can finally write that V final square is U naught over M. And V final is equal to the square root of U naught over M. This problem here is a little bit more challenging than the previous one that I introduced to you because it involves a second equation, involves a system of equations, a system of 2 equations, one of conservation of momentum, the other of conservation of energy. Okay, What time is that? 11:45. Any questions? There are, so we have done 4 examples so far. Okay, real life examples of an explosion, right? No, the case of a gun and a bullet, a cannon and a cannonball, a gun and a bullet being fired, and a cannon and a cannonball. Okay. Do you notice that when they fire the cannon move backwards? The same thing happens with a gun, right? So is the bullet or the cannonball reacting with the gun and the cannon respectively? Newton's third law being applied. So here you go. So far, we looked at 2 different types of collisions. I'm going to put it collisions between quotes, okay? The first one is inelastic collision. The second one is an explosion, the reverse of an inelastic collision. And the reverse of inelastic collision. There is one more important type of collision that you must know. This type of collision is called totally elastic collision. By definition, a totally elastic collision is a collision where the mechanical energy of the system is conserved. Okay, initial mechanical energy is equal to final mechanical energy. Okay. In the case, in the first 2 cases we studied, mechanical energy is not conserved. Okay. I call that potential energy, but it's not exactly potential energy. This thing that you see here that I christened as being potential energy, this is actually a non-conservative force. Okay, it's actually energy related to a non-conservative force because it's an explosion. It's the chemical energy of the gunpowder that's propelling the 2 objects. Okay, and we can prove that it's easy to prove. Okay, it's easy to prove that in an inelastic collision, it is easy to prove that mechanical energy is not conserved. In the first 2 cases, we studied mechanical energy is not conserved. Okay, example of elastic collision. Of an elastic collision. If you have played pool table, right? The balls in the pool table, they undergo totally elastic collision. They do not stick to each other, right? It's not inelastic. Instead, it's a totally elastic collision. And both energy and momentum are conserved, okay? And we can come up with another example. Example 5. This is going to be a little bit more challenging because we have to deal with the second equation, the system of equations, just like we had for the explosion. Two objects having the same mass undergo a totally elastic collision. After the collision, object 1 bounces off object 2. Object 1 has an initial velocity v01. That's known, and object 2 is initially at rest. Find their final velocities. Consider the surface where they move to be frictionless. Here you go. That's is going to be an illustration of totally elastic collision. Let me get that for you. Go. The explosion, right? Do I need that? Let's assume that we're going to need that for now. What about this other one here? Yeah, let's assume that we're going to need that. Most likely we won't. Okay. Okay. This one is a totally elastic case. Okay. Here you go. Totally elastic collision. Mass, same masses. One moving towards the other. One push the other pull on the. One push, the other pull. And then they end up moving with a final velocity. Okay. In the case of the pool table, we have something similar. Initially at rest. One ball is going to collide with the other, right? And here I'm going to, I'm going to explain very soon what that is. Okay. That doesn't happen in real life, right? But mathematically it's possible. You're going to see why I illustrate that. Okay. So let's take a look. Let's look at our equations, right? Here you go. Solution. Initial momentum is equal to final momentum. Initial mechanical energy is equal to final mechanical energy. The objects are not changing height. Consequently, the final potential energy must be equal to the initial potential energy. And what is left is just conservation of kinetic energy. Right? I can elaborate on the first equation. The first equation is momentum of the first plus momentum of the second on both sides. And then I elaborate a little bit more. Let's keep on moving here, right? Two masses. The masses are the same. mv01, mv02, right? The second mass is at rest. mv final 1, mv final 2. Like that. Initial kinetic energy is going to be half mv01 square half mv02. Oh, wait a minute. I have to have my let's see. Let's go step by step, right? Instead of initial kinetic energy is going to be initial kinetic energy of 1 plus initial kinetic energy of 2. Final kinetic energy of 1 plus final kinetic energy of 2. Like that. See, I'm doing side by side. System of equations. Two systems of equations. This one is going to be 0 because the mass is at rest. And I do not know what's going to be VF1, VF2, okay? This is not an inelastic because this is not an inelastic collision. VF1 is not necessarily equal VF1 VF1 is not necessarily equal to VF of 2. Okay? But this one here, this term will definitely be 0. Kinetic energy, initial kinetic energy of 2 is going to be 0 because the object at rest. And this is going to be half m v naught 1. 4 more minutes to go. Half m v final of 1 square half mv final of 2 square. Like that. I want to know what's going to be VF of 1 and VF of 2. Okay, let's move. Keep on going here. We do know V naught of 1. We do not know VF of 1. I'm going to emphasize that by, this mass here is not in its proper place. Let's put it here. Here you go. I'm going to emphasize it by both facing it. I'm going to both face both and change it VF2, right? Here you go. Both face it. Both face it. Those are the unknowns. 2 unknowns, 2 equations. 2 unknowns, 2 equations. In principle, we can solve. We may solve this system of equations. 1157, right? Now, let's do some simplifications. Mass cancel out. Half cancel out. This 0 is not supposed to be here, right? This 0 is not supposed to be here. And the mass cancels out too. Okay. Because it's one-dimensional collision. Because this is 1D collision. The vector symbol can be removed, right? But we're still going to keep the bold face there. V, V, V. Oops. V, okay. And now how do we solve this problem? We solve this problem by eliminating one of the unknowns. Okay, there are a bunch of techniques out there. Let's eliminate VF2 by passing VF1 to the other side. Yeah? Once you do that, you substitute VF2 right in here and solve for your problem, okay? And that's what I'm going to do next. What time? 11:59. There's still time, right? Let's see what's going on here. Yeah, take it out. I'm going to replace right in here V naught 1 minus VF final. Here you go. And we do have a square. Get here, right? We can expand this term. We're going to get a square, V naught 1. We're going to get a square, V final 1. This sign is going to be positive, but then we are going to have the cross term, V naught 1, and V final 1, right? Not bold-faced. The only one that is bold-faced is going to be the V final 1. What time is that? 12 noon. Okay, what I'm going to tell you, you can finish that at home. I am going to tell you that the solution for this problem is going to be V final of 2 is going to be equal to V not 1. But there's more stuff to do, right? Try to do that yourself or look at my notes of 2023 that I have the in-between steps, okay? So that's what happens whenever two masses or two objects of same mass undergo totally elastic collision. You know, their velocities are swapped. The first mass comes to rest. Here you go. The first mass comes to rest and the second mass starts moving. Here you go. See? That's how it happens. Here you go. P naught 1 collide with 2. 2 is at rest. 1 becomes at rest, and V2 and the second object takes off with the velocity, with the initial velocity of the first one. That's what the solution is all about, okay? We can stop here now, and I have office hours. And if you want to stay around, I'll be here, okay? So I see you on Wednesday. Let's stop here. Are you there, Stephanie? Okay, so